computer. Okay, so we've started. Okay, well, thanks everyone for coming. Hopefully the Irish in the crowd aren't suffering too badly from the Paddy's Day weekend. So yeah, so this is the third workshop in the series on kind of Bayesian statistics and using a real life example, which is essentially buy till you die models, which is kind of a pretty common, from what it appears. Now I'm not in retail, so I can only go on A, what I've heard, and B, what I've read. And it seems that buy till you die is a pretty common metric. It's a subset of a broader category called RFM models, which are recency, frequency, and monetary. And this is one particular type of RFM model that's used. And I got into it last year, and I appreciate I'm going over old ground. I got into it kind of last year when we were doing our data science soup to nuts, but I realized it was kind of too sophisticated and there was too much going on for the purposes of what I was trying to do for that series. So I kind of said, I'll park it. I kind of mentioned it briefly. There was one workshop on it, which is ironically one of the workshops from last year that has gotten the most views on YouTube. I was just looking at it the other day. I pay no attention to the YouTube views at all. But it had a couple of hundred and I was surprised. But I guess buy till you die is kind of like it, because people use it and it gets, you know, YouTube, I guess it's a term that just gets clicks. So yeah, I was, because it was probably the least important of that series, and yet it's the one that has, certainly if not the most, it's definitely the second highest, which I thought was a bit odd. But the basic idea is that so Bayesian statistics is a way of using essentially a combination of prior knowledge and data to come up with what's called a posterior. The key thing and why it's different is that it tries as intellectually kind of honest and consistently as possible to capture and articulate the uncertainty that we get. So it captures this parameter uncertainty. So when you fit a model, you're not just coming up with a point estimate, you're actually coming up with a distribution for each of the parameters of the model. So to give a quick example, let's say, for example, we have a bunch of measurements of a population. We don't, in kind of old school, we would have just calculated a mean. With Bayesian statistics, you give a distribution of possible means that the sample could represent about these. So you kind of, it's got that kind of inferential aspect to it. I'm sure most of you here know what Bayesian statistics are. Does anyone, like, I see a lot of familiar faces, but I am conscious there's one or two new faces. I'm going to assume most people have a basic knowledge of what Bayesian statistics is, at least, and that's why you're here. If anyone doesn't, can you just, I have the chat up here and I can't see the participant list. Will everyone just, if you have any questions or anything like that, please pop them into the chat. I'm more than happy to kind of go on diversions and stuff. That's why I set these things up to be about 2 hours long. So if you have any questions or anything like that, and if I'm making assumptions and people need me to explain something, it's great to get feedback, to be quite honest, because it can be a bit disconcerting talking at a screen for 2 hours. So any and all feedback, even just simple messages in the chat, is highly appreciated. So please don't be shy. And if you need me to go over something or ask about anything, just please let me know. Okay, so I'll quickly summarize where we were, like what we did in the first two workshops. So we had, the first workshop was very, very simple. It was just kind of taking the data and, you know, going through, discussing it. So basically what we have is, it's the original data set we have, and this is from last year, we have like transactional data. It looks like this. Now, for the purposes of what we're doing for this, certainly it's probably going to be for at least a couple of more workshops. We're not using this actual data because we don't know what the real answers are. What I've been doing so far is kind of using the model, the statistical model that we have to generate data, and then essentially try to refit the model back to itself. So essentially trying to make sure it's inverted. And while that, and then seeing, can our model recover the parameters we use to generate the data? So it's kind of a toy example to an extent, but it it comes with a couple of pretty major advantages for the purposes of what I'm trying to do here. The big one is that we kind of know the answer, and we also know that the model we're trying to fit is the actual underlying generative process that produced the data, which in most cases is not the case. So whenever we fit a model, we're making assumptions about how the data was produced, and that is usually just a simplification of reality. Whereas in this case, we don't have that problem. We actually know that our model was produced using that statistical model. So what we're essentially kind of sanity checking our model to see, given data that's the model is used to produce it, can it essentially recover itself? Because if it can't, then you're in trouble and you know that you have a problem. Because if it can't work on data that's actually generated from the model, how good is it going to be when you know that that's a very simplifying assumption? So I hope I'm not getting too technical there, but that's basically what we're working on for this model. And basically in marketing, the way the things work are, like I said, most of this stuff is based on the RFM modeling, which is recency, frequency, and monetary. For the purposes of what we're talking about, we're not going to really talk about monetary yet. We will get to it towards the end of the workshop, depending on how well we go. But what we're trying to do here, recency is essentially how recent was the last transaction, because in marketing, that's usually a very important metric. So customers who transacted more recently on the site are actually more likely to A, still be customers, and B, are more likely to actually transact again in the near future. So there's a kind of a recency bias there that's inherent. This is just kind of the nature of customer kind of transactions. Now, if you're using these kind of models in a different area, and for those of you who are here who come in from the world of insurance, I actually do have a possible place in terms of loss development where this could be of interest. I think this might actually work in a certain, I haven't tried it out yet, and I haven't got the data to work on it yet, but I have a funny feeling these kind of might work in other areas. So obviously some of these underlying assumptions would change in that case. But certainly in retail, recency is really important because you kind of want to know who your most recent customers are. And then frequency is just a count of how many transactions you've had. So that's when it's a slightly different use of the terminology from my point of view. I wouldn't think of frequency as a count of transactions. I would think of it more like a rate. Although I guess to a certain extent, they're the same thing, for a given unit of time. But that's what the buy till you die model does. Now we're not really building buy till you die models yet, because they have both this, like I said, this transaction frequency and the churn customer lifetime kind of aspects combined together. And we have kind of decoupled them for the purposes of what we're doing to just gain a foothold. So what we've done is we're looking at the transaction frequency, the transaction part of it first, and then we're going to look at the lifetime, the customer lifetime part of it. And we're creating, very kind of, what would you call, kind of trite synthetic data sets that make farcical assumptions. Like, for example, for the transactional frequency, our first data set is just going to be a year long, and we assume that everyone is transacting the whole year, and we're not really worrying about people not transacting, if you know what I mean. We're not worrying about churn. This is just going to last for a full year, and all we really care about in this case is customer transaction frequency. Okay, and then we will flip it the other. When we're dealing with lifetime, we give every customer a single transaction rate, and we just use the transaction rate, and then we use that to kind of figure out what the customer lifetime kind of modeling is, and getting a sense of how long the customer is active on our system. So we're using these kind of very simplifying assumptions that are not particularly useful from a real world point of view, because they're just too simple, and they don't really, like, the data that we've got are so far away from these assumptions that essentially any modeling we would do on it would be useless. But they are essentially Lego bricks to combine together that allow us to get a better understanding of the buy till you die model. And part of the reason why I know that is because this is what I've been doing to try and understand buy till you die, and in particular the Pareto negative binomial distribution. But I will talk about that a little bit later. So that's basically the background for where we go, and that's the modeling. But what I'm also doing is using this as a way to teach the Bayesian approach to this. So like I said, rather than having a single estimate like you would on a more kind of traditional approach, you would have point estimates for every customer transaction frequency. In this place, we're actually going to have a distribution of frequencies. So, and the reason why that is valuable is, excuse me, because I'm talking for so long, I have a big mug of tea here that will be lubricating my voice. The reason why that's so important is because, especially now in this case, I mean, I think it's important in general, but when you think about it in terms of low data, so let's say like low frequency transactions, which customer transactions typically are on an individual basis, you know, the frequency of transactions is typically quite low, right? You can actually have a relatively wide uncertainty band, like on relative terms. So to give you an example, let's say, for example, you have a customer that over the period of 2 months transacts once on your system. Well, that's essentially, if we're going on a weekly basis, right? And that's the unit I've used in this case. Let's say we go on a weekly basis, that's one transaction in 8 weeks. Okay, so the maximum likelihood estimate of that is about 0.125. But if you actually run any simulations, you could very easily get one transaction with a rate of 0.1, right? Or 0.02, or 0.2, or even 0.3. And, you know, the range of values there, in absolute terms, they're not big. But in relative terms, the higher end of that credible interval is like 10 times higher than the low value. So you've actually got a range of an order of magnitude in your underlying frequency. And that can be really important information to know because, you know, again, in absolute terms, there's not much of a difference. But, you know, if you've got an order of magnitude difference in your estimated frequency rate and all of them are credible based on the data, capturing the uncertainty in these inferences is really, really important. Certainly in a lot of the work I do. Now, maybe it doesn't matter to you and some of the stuff you're doing, it won't really care. But I think in really critical things where these things are very important, it's important to maximize your use of like these methods as much as possible. And that's why summarizing this information as posterior distributions rather than point estimates is very important. And the other key thing from that is a point estimate gives you one value. And generally, when you think about uncertainty, you think about symmetric intervals around that point estimate. But quite often you have a skew. So in my example there, let's say, for example, it can go from anywhere from 0.3. We look at our posterior distribution and we go from 0.02 to 0.3, right? Well, the median estimate, like the maximum, well, not the maximum, the average value within that distribution, the mean of that distribution could be, say, 0.1, right? So that's not a symmetric distribution around the midpoint. So the maximum, sorry, I'm getting caught in terminology here. The expected value of the transaction rate is, say, 0.1. But in terms of the credible interval that you were looking at, say 80% or whatever, it could go from 0.02 to 0.3. So it's not a symmetric distribution around that. And typically, because we think in terms of normal distributions, we typically think in terms of symmetric regions of uncertainty. But certainly in a lot of the work I do, these things are highly skewed. So, and that's also very important because, you know, you can have a massive, especially when you go out into the tail, you know, going slightly wider credible intervals can really widen the range of potential values within that credible interval. So that's kind of what all these methods essentially try to capture. Okay. So before I get on, I like I said, I recognize a few names, but I'm always very conscious that we get new people from time to time. Does anyone have any questions kind of before I start with what we're doing? And I'm kind of going to summarize where we're going with all of this, and I'll go over kind of the last couple of weeks. But if anyone has any questions, like please pop them into the chat and about anything I've said, or if anything that I kind of am using terminology or anything like that, I'm keeping an eye here. And like I said, I would appreciate any questions just to make sure that I'm not just kind of, you know, talking to the screen. Okay, so in Bayesian statistics, like I said, we have a prior distribution and then we have a posterior distribution. And the old way that this was done was through the use of conjugate priors. Now, I talked about this a lot more in the previous workshop, so I'm just going to quickly go through it again, but I'm not going to talk in too long about it. But the basic idea is that there's these, when for any given likelihood model, which is essentially the model that we use to describe the data, you also have, most likelihood models have an equivalent, kind of a partner distribution which is called the conjugate prior to the likelihood. And essentially what it does is it means doing that integral of combining the prior and the likelihood, which is essentially an integration. It reduces that down to doing some summary statistics on the data and modifying the parameters of the distribution accordingly. And in this case, basically, if we have like a gamma, so if we're dealing with a Poisson distribution for count data, which is, you know, a pretty common way of doing it, and we have a gamma prior. So the prior has two parameters, the shape and the rate, which is R and alpha. Well, then if we observe X events over a period N, then we just add X to R and we add alpha to N. And that gives us our posterior distribution. And we did some work on that, and you can see, so for a given set of examples, you know, how does that work, and, you know, all the updating. If any of you looked at any kind of Bayesian statistics before, you will find, you know, this is all pretty standard stuff. And the reason why that was so useful is it meant we didn't have to really do much computation. So these were very, very popular. First, when Bayes came around, and when statistics was, well, I don't want to say invented, but when statistics became very popular in the early 20th century with people like Spearman and Fisher and all those kind of guys, Neyman, Nyman, I'm not quite sure how you pronounce his name. You know, you had to use mathematics back then because computers didn't really exist. So mathematics was essentially the language that statistics was discussed in. So you had to use mathematics, and they had this, you know, mathematicians had discovered these conjugate priors, and they had interesting mathematical properties. And essentially a lot of the more weirder probability distributions that are out there are essentially, from what I can tell now, if there's a statistics historian in the crowd, please correct me on this, but some of these appear to have been developed as a way to create conjugate priors for like given likelihood models. So that's why they kind of got used. And, you know, that was kind of the way you did Bayesian statistics. Now, no one really did Bayesian statistics. One, because in many cases, if you weren't using your conjugate priors, then you were kind of goosed because it was just too computationally expensive. And in many cases, you know, the conjugacy wasn't the most appropriate, what do I want to say? It just wasn't the most appropriate way for this data, whatever it would be, to be described. And secondly, it was a very human thing, is that the two guys who were huge in early statistics, which was Ronald Fisher and I can't think of the Neyman guy, who was essentially his son-in-law. They hated each other. They worked together for a while, and then they ended up hating each other. And the only thing they kind of agreed on was that Bayesian statistics was terrible. And it had this whole thing of that it was not very scientific because of this prior information. So therefore, it wasn't as scientifically pure. You weren't just letting the data speak for itself. Now, going down the philosophical route, I don't want to kind of, you know, go over old ground. A lot of that is kind of realized to be flawed now, and, you know, Bayesian statistics is shown to be very, very useful. But the other big one, I mean, I think those could have been overcome, but the big thing was it was just too computationally intensive. And it's the reason why Bayesian statistics has become so powerful, even in the last, say, 10 years, I would say, has been the rise of computational like capabilities, not just faster processors, but also an awful lot of work has been done in numerical computing and statistical computing, and, you know, just algorithmic research and all that kind of stuff to enable some very powerful stuff to be built. And a lot of that is encapsulated in, for example, STAN, which is the Bayesian computation engine that we are using during this workshop. And it allows us to basically create, at least in theory, any likelihood model to describe the data that we want, and at least attempt to fit the model. Now, just because you've written a likelihood model and you've thrown data at it doesn't mean that you can like get answers that make any sense. And we're going to discuss, I'll discuss that why, you know, over the course of you know, as we're talking. But it actually gives you, it at least gives you the capability of doing that. And that, you know, that can be particularly useful. All right, so Enough waffle. Right, I've been blathering on for a while now. So ultimately, what we have here is we have a whole bunch of customer data. Let me just show it to you here. And now this is our synthetic data set that I'm just kind of showing here. So you can see we have this, essentially random. This is all synthetic. There's a model here that actually generates the data. You can see generate transaction data sets. I'm not going to go through it for the purposes of this, but you can see all the code to generate this data is in there. So you should be able to recreate all the materials in this workshop pretty much perfectly, because I set seeds and all that kind of thing. And we have a random customer ID. They've given them a cohort number. You can ignore that because that will come up later on in the workshop, but I've included it for completeness. We have a transaction timestamp, so when the transaction was ran, and then how much currency was paid, like what was the amount of the transaction. And I have about 700,000 rows in this data set. And like I said, it goes throughout the whole year, and customers transact from essentially the start of 2019 to the end of 2019. And as I mentioned before, there's no lapsing, there's no churning, there's none of that stuff. We're completely ignoring that for the purposes of what we're trying to do here. We're just trying to get from a practical point of view. You don't have everyone starting at the same time, and there's all that real world stuff, which is hugely important to what we're trying to do. But for the purposes of, it says my internet connection is unstable. Okay, seems to be back. For the purposes of what we're trying to do and just get the inference, that's perfectly fine. And we will incorporate combining the transaction part and the lifetime part later on, and that is essentially the various forms of the BTYD models. Okay, and I'll get into all that like in a workshop or two. Okay, so I think, let me just, so is everyone following where I am so far? Let me just look. Can someone, Neil, if you would, as long as I haven't lost my connection or whatever. Oh, I've got a few thumbs up. That's great. Okay. Yeah, I'm a bit needy. I need a little bit of attention from time to time. So and also to make sure that my internet hasn't died. Right. So we have a whole load of data. We've take out 1,000 customers that we've kind of created this fake data set, and we've essentially created very simple customers. We've essentially got how many transactions were made and over what period of time. We have a few different ones, and now we're going to fit a model from that. So this is the standard language here. I'll explain what's going on a little bit later, like what's going on under the hood. But before we kind of get to all the nitty gritty of how Markov chain Monte Carlo works, I kind of want to dive straight in and at least give people context before I bamboozle you all with the science and what's going on in the background. And we can't unfortunately ignore that. We can't just kind of hand wave and say this is magic and it works. It's a power tool rather than a black box. So power tools are really, really good, but you do kind of you handle them with caution, and B, you kind of have to know what you're doing, and that is very much the case here with Stan. You kind of have to understand at least the basic principles of what's going on. So I will be explaining that, and I'm not just explaining it out of some idealistic sense of theoretical completeness or anything like that. This stuff gets very important and has very real effects on how things work. So basically we have, and just to explain, is anyone here, actually, just to ask before I go into too much detail, is everyone here at least got a basic familiarity with how these kind of Bayesian computation things work? So if I say like Hamiltonian Monte Carlo or Markov chain Monte Carlo, is everyone kind of familiar with those concepts? I'm happy to explain it very briefly if anyone does. So if anyone doesn't really understand how any of these things work, please just put something in the chat and let me know. If you don't want to put it in the global chat, just direct message me. I'll try to refrain from calling your name out. But I'm going to assume that the basic understanding of, you use your data to create a target distribution, and then you use Markov chain Monte Carlo to essentially sample from that posterior distribution. So and we talked about this a little bit more in the previous couple of workshops, and I don't really want to spend half an hour going through it again, because it's one of those things. I'm happy to do it, but I know myself, I'll end up spending half an hour doing it and we'll really get nowhere. But I will totally do it if we need to, but if we don't need to, I won't. Okay, no one's pinging out. Okay, so I won't get into the nitty gritty of how Stan works, but that's basically what we're doing. And the way Stan is it essentially turns a file like this into a C++ code. The C++ code then runs the fit, like the fitted it creates an executable file. That executable file essentially has code that runs the sampler, and then you pass data in with an execution of the sampler. You pass data in, and it creates the posterior distribution data. And that's a very high level of what's going on here. And the input to the Stan is a file like this. So we've got a couple of different blocks. The last one here, generated quantities, I've included for later. We don't really need to worry about now. The main ones I want to talk about are data, parameters, and model. Okay. So the data is the input data into the model. So essentially what we have are, like I said, we have 1,000 customers, right? We have a time that we observed information, and then we have the count. And essentially what we're going to do, like in maximum likelihood estimate statistics, we would just divide the count by the observed time, and that would give us our frequency rate. Okay, and that would be absolutely fine. And you know, that could absolutely work. That would work fine. And you know, we'd be no, you know, we wouldn't be particularly badly off. But in this case, like I said, we're doing something slightly different. So this is essentially we have to pass the data in. So we need to pass in how many data points we have. So the count of the observations. So in that case, it's n. And then we have an array of counts, which is integers. And you can see the lower bound of 0. We don't actually technically need that. It doesn't have to be bound below by 0. But it's one of those things that it's true. You can't have a negative count. So therefore, you shouldn't allow negative counts. And it means if you accidentally pass them in, it'll throw you an error. And that's kind of one of those kind of defensive programming ideas. And it also gives you better statistics, because you know these things, these constraints can be important, so you should include it. And it's data being passed in, so you know it would throw an error later on anyway if you tried to, but it's just a handy quick way of saying I'm giving you bad data, and it usually lets you know that you've messed up further up the data pipeline. And then similarly we have a count of times in weeks, which is a vector, because it doesn't have to be an integer now, because it can be a continuous measurement of time. And again, we have a lower bound of 0, and it's a size of n, and it's the number of weeks. Now, the reason why they're in two different forms is basically we prefer to use vectors whenever we can, because there is a lot of code in Stan that is vectorized, so like matrix vector multiplication. Whereas arrays aren't. Arrays are kind of a more general array ID. You could have an array of vectors, for example, but you can't also vectors have are not integers. So it's just kind of a defensive way of making sure that we're not accidentally passing in non-integer counts. Okay, and then we have one set of parameters in the parameters block. So these are the parameters that we're going to do inference on. So every customer gets their own lambda value, and again, a lambda cannot be less than 0, so we put a lower bound of 0 on it. And there's n, which is 1 for each customer. So essentially we're getting, let's say for the sake of argument, 1,000 customers. For each customer, we have a reading of how many transactions they made in the time period and over what period of time they were observed. So in this case, it would be a year. And we then pass that data in, and then I'll get to how it's done, but we know that the output of that is every customer is going to get a lambda value, which is going to be essentially the posterior estimate of the transaction frequency of that customer. Okay. And then finally, we have the actual model, which is what we would call the likelihood model. So we're basically saying that every observation, so this is kind of this part here. So we're basically using the bar. So we're saying we observed this value here, BTYD count, and it was parameterized by this value here, which is the transaction rate times the number of weeks we observed. So in each case, the lambda is going to be on the scale of frequency per week. Okay, if we didn't include that, then each lambda would have a different scale because it would be the lambda that the period of time that the customer has observed. So by including the number of weeks in this part of the calculation, we actually get a normalized lambda, regardless of how many weeks the customer's transactions were observed over. Does that make sense? And then we can run. Now this works. I've called this the flat model, right? Because we do not have a prior here on our lambda, okay? And this is really bad practice, but I'm doing it just to show you. So effectively what we're doing here is we're fitting 1,000 separate models, which someone who was in the workshop last month pointed out that, you know, we're not doing anything particularly clever here because we know that every customer, essentially this would be the exact same as running one customer into 1,000 different stand models. We would get the exact same output, okay? Because, you know, there's no connection between them all, right? Now, there is an implicit prior on this, right? Now, even though we haven't created an explicit prior for lambda, there is an implicit one, because if you don't include a prior on lambda, it basically creates an what's called like the uniform prior. It puts a uniform. So it basically says every possible value of the distribution is equally probable, right? So in this case, because we've set lambda to be the lower bound of 0, it's basically saying any value for lambda from 0 to infinity is equally probable, right? Now, if we didn't have that lower bound on lambda and we got rid of it, it would basically say any value from minus infinity to plus infinity is equally. And similarly, we could put ranges on it if for some reason we had a lower bound of 0 and an upper bound of 10, which I'm not sure why you would do. If there was a reason why someone could never transact more than 10 times a week, say you had some kind of limit, then you could actually put that in there. And that would say every value between 0 and 10 is equally probable, right? And that is typically how we would work using maximum likelihood estimates, right? You don't have this prior distribution on lambda. Now, that immediately, while that sounds really good, okay, if you think about it for a little while, you realize it's problematic. Now, it doesn't throw up any issues with this particular model, and I'll talk about that in a little while. But from a logical point of view, which we'll get to in a few minutes, it also kind of doesn't really make any sense, right? Because what you're saying is that regardless of the situation, like a frequency of like 10 million is as likely as a frequency of 0.1. And a moment's thought will realize that that's just pure nonsense. That it's kind of nonsense to say that, and this is also why uniform priors are generally bad, because they put positive probability mass on completely unfeasible parameter values, right? And that can actually mess up with your inferences. And while it doesn't really affect on the frequency side, we will actually see that when we include uniform priors on the lifetime side, it blows up the model and we can't actually get anywhere. Every single thing just explodes. And it will become obvious why when we talk about that. But I just want to get that out there. But for the moment, we're just going to ignore that fact. We're just going to fit. And we did all this in the previous one. We're running our chains. You know, this is just the output. I'm using command stan R for this. We're producing the fit of the data. We're just going to look at the outputs. We want to check these. We do, however, need to check what are called HMC diagnostics. So one of the issues that you have, I mentioned earlier that Stan and Bayesian statistics and all this is a power tool rather than a black box. And the reason why I want to say that, like I said, you kind of have to handle it with care and you kind of have to know what you're doing, is that these methods are they force you to be very, very explicit about what you're doing, right? Whereas with a lot of, you know, pre-existing algorithms and models that are out there, kind of the likelihood model and all this kind of stuff is baked in and you just kind of throw data at it and you get an answer back. However, because of what we're trying to do with Bayesian computation, we're not actually just looking for a single number, which in many ways is an easier thing to do. Because when you're doing like things like maximum likelihood estimates, or even in the Bayesian world, the maximum a priori point, you're essentially trying to find an optimal value, which is like the point of highest probability density or whatever, or some kind of optimal point estimate of the model that we've set up. with what we're trying to do, we don't necessarily care about point estimates. What we're actually trying to do is get some sense of the topography of the probability distribution. We're trying to get a sense for the shape of it. What does it look like? What are typical points from it? And that's why what we get back is essentially a sample of all the points from that probability distribution. Okay. Now, as I mentioned, there's 1,000 customers in this data set. So there's actually 1,000 parameters in this. This is a 1,000 parameter probability distribution. All right, that are all kind of coming together as a single value. Now, they're all quite independent to one another. So the value of one doesn't really affect the value of other, not in a very, very direct way. That's actually a good thing. But we still are trying to sample from 1,000 dimensional space, which is what Stan does. And I will talk a bit more about how it does that a little bit later. So that's what we're trying to do. And we're not just trying to find one value that's somehow optimal over the rest. We're actually trying to get, a sample of values from this so that we get a sense of what the probability distribution looks like. And that is a much more computationally intensive problem, first of all. But secondly, it's also it's not just computationally more difficult, it's also a more demanding task conceptually. And the reason why I say that is because if your model is flawed in some way, like if you created something that's wrong, like you're fitting a completely inappropriate model that doesn't really describe the data you've observed at all, you're going to get weird stuff happening when kind of those two separate realities collide together. And what happens is that the numerical algorithms that are used to draw that sample from the posterior distribution fall over, right? And that's what's called a divergent transition. And essentially what's happening is the sampler in like Markov chain Monte Carlo, it's trying to move from one state, like from one point in the posterior space to another, and it can't do it properly. It gets basically numerical errors because it's essentially a physics simulator. And like I said, I'll get into all that a little bit later. But the whole thing falls over. It falls over. Okay, sorry, I've just got a question there. When you generated the customer data, did you sample from the same distribution for each of them? Yeah, yes, I should go over that. So basically what I did was I used the underlying idea. So every customer was assigned a lambda from basically a gamma, although we don't have that yet. We'll get to that in a minute. So I basically created like a hyper distribution of potential lambda values that every customer could get. Every customer was assigned a lambda value, and then we generated the transactions off that lambda value. Okay, and I started them. They all had the capability. Basically what I was running it was rather than a Poisson, I was using an exponential to get the times between transactions using that rate, and I would just basically get those time differences. So every customer was transacting for a year, but obviously the different transaction rates meant they had different timestamps at which they were transacting and different gaps between them. So that's why every customer has a different period, essentially a different time period that they were observed in, but also a different customer count. But the benefit of that is that I know what the true value is for every customer. So when we create our sample from Stan, we can compare it back to what we know the true value is. And that way we can tell, is our model actually capable of recovering the parameters that we used to generate the data? And like I said, that sounds like it's an obvious thing, but it's not. And actually, in some of these models here, we're going to have to do some jiggery pokery to allow that to recover it. Okay, so yes, so I think that answered the question. So each customer has a unique frequency, but those frequencies were all generated from a single hyper distribution, if that makes sense, which we didn't have to do, but that's kind of the basics of what these statistical models are based on. And it kind of makes sense. And it's a way of getting like information about other customers from your existing customers, if that makes sense. And that's kind of why they do it. So essentially each customer has a unique transaction frequency that we are trying to recover from our model. Okay. Okay, so like I said, because we have because we have this sample from 1,000 parameter distribution, and like I said, we may create a likelihood model that doesn't explain the data very well. And as a result, we can have all these computational issues. And there is an old joke, there's an old saying, there's the folk theorem of statistical computing, which is kind of pioneered by a bunch of guys online, like Andrew Gellman, who's kind of one of the kind of thought leaders behind Stan. He says that essentially computational issues tend to be modeling issues in disguise. So you have problems with your model. A model is a model. It's very hard to say if it's right or wrong until you try it. And then when you try to fit your data using your model, you have all these computational issues. You have like convergence issues and all this. And these were actually well known when, like, we'll be using this to build hierarchical models. There were like convergence problems with what were called like mixed effects models, which are essentially hierarchical models. Convergence issues were always well known. And what was often happening was that the model you were trying to fit was a poor description or needed to be changed somehow to match the data you've observed to get a better fit of the data. And that was why there were so many convergence issues with a lot of these problems. And that was kind of pretty common. I remember like 10 years ago when I first kind of starting, I've been using R for since the late 2000s, so like 2008, 2009, but I kind of got into it in a big way in like 10, 11. And I remember reading stuff on the various R forums and they were talking about convergence issues. And that is kind of, you know, that was what's going on. When you look into it in most cases, you find kind of after the fact, oh, actually, what happened here was we had issues with, you know, the model was a poor description for various reasons, or it could be just, you know, numerical issues with you're dealing with, you know, finite precision on computers and all those kind of things that numerical computational people like, you know, computational fluid dynamics and all that, they've been dealing with all these issues since the 50s. It's all that kind of stuff, but it's cropping up in different places, and there are things you have to account for if you're trying to use them. Okay, so yeah, so basically what we have to do is we can't just take our model fit, like our sampler, and then look at it. We also have to look at, you know, what has happened since. Now I've got these issues here. There's obviously, I've just reran this data. Maybe I should rerun this after this workshop. I've just noticed these in the last time. Might clear my cache, but we have to check these things. Now we will go into this in a bit more detail once I explain Stan and what's going on there. But essentially, what you don't want, the tree depth is an efficiency thing. If that isn't good, it generally means you can generally improve your model and make it more efficient. And by that I mean you can, you know, execution time is reduced, which is always good. The big one here are these divergent transitions. So what happened is the best way to explain a divergent transition is, imagine you've got a physics simulation of the sun around the Earth around the sun, and you're tracking out that simple like two-body problem, but you haven't done your numerics properly. So as a result, like it basically ends up spiraling in towards the sun, and it gets closer and closer and closer. At which point the distance which you're dividing by underflows or overflows, and you just get this crazy number, and the whole thing goes nonsense. That's kind of like what a numeric a divergent transition is. Essentially, there's a problem with the geometry of your model, which is how you've set your model up, and as a result, the numerical integrators and stuff that are trying to like fit the data can't deal with it properly, and it starts throwing out silly numbers. And Stan essentially detects that and spits out warnings. Now, a lot of people complain about this, but these are hugely important because it tells you if you have divergent transitions, it means that the sampler that you've set up is not able to sample properly. There's regions of the posterior space that the sampler isn't able to get to. And your problem there is you don't know how important that region it can't get to is. It could be really important. It could be not important at all. It could be 90% of the probability mass. It could be 10% of the probability mass. It could be a negligible amount, or it could be most of it. You just don't know. So as a result, you kind of have to have a zero tolerance policy for divergent transitions. If you have any divergent transitions at all in your model, your sample is biased. And you don't know if the parameters that you've recovered for your model are actually representative of what the sampler is doing. Now, this isn't a conceptual thing. This is that your sampler is not producing a valid statistical answer. And this is an additional step that you don't really deal with when you're in the maximum, like when you're dealing with point estimates, because point estimates don't care about that as much. It's just one value. But in this, we're looking for a distribution of values. And essentially, if we're only looking at, say, 30% of the probability mass, then our distribution is biased. And this is a very, very real problem. And it was actually first discovered, it was this kind of problem which was one of the motivating factors for the development of STAN. And it was essentially, I think it was, I'm telling this story and I'm probably perpetuating nonsense, but I'm going to tell it anyway. My gut, I think I read somewhere that Andrew Gelman was going away somewhere. Like I said, he's the guy at Columbia who does a lot of this stuff. And there is kind of the canonical hierarchical model value called the 8 schools problem. I won't bother getting into it. We can explain it some other time. But it's a really, really simple set of data. And it's basically, it's a mean and a standard deviation of school values, school tests. And there's 8 schools. So each school has like a mean and a standard deviation. But it's a hierarchical model because rather than treating each one, we say each distribution has a hyperdistribution. And it's kind of the canonical hierarchical model that gets used. And it was fitting JAGS, which is kind of the previous MCMC software. And he left it running for a long, long time over like a bank holiday weekend or over Christmas or something, because he just wanted to see what would happen if he did it. I think it was just a random curiosity, or he forgot to turn it off or something. I can't quite remember. But when he came back and looked at it, he noticed that once you plotted things for a very long time, every so often the sampler would just flatline and it would get stuck at it. What it was saying is basically it was in a particular point and it would try to move to a new point. It wasn't able to. So it would flatline and it would stay in that point. And it would do it for a long, long time before it finally found a transition that was valid and therefore jumped out and kept going. And that is typically a sign of a problem. And they didn't really know what was going on. And they basically found that essentially there was problems with their model. And that kind of led to the use of HMC, which has very strong diagnostics for these problems and allows you to try and kind of help you, tell you at least there's a problem. Sometimes it's not great at telling you how to fix that problem, but we'll talk about that in a future workshop. And and that's kind of how it, that's basically what led to that. And that is really valuable because if you get these divergent transitions or this EBFMI, you know that there's some kind of problem with your model, and therefore that you should not rely on the answers that the sampler has produced for you, because it is not a statistically valid sample of the posterior distribution you have created, because it's biased. It's only recovering values from a subset of the entire posterior, which means you've got a biased data. So to explain what I mean by that, let's say, for example, you're trying to get an estimate of the heights of a population, and for whatever reason, you can't properly explore where people's heights are above 6'2". Well, your estimate for the overall population mean is going to be biased to the downside, because you can't really explore where the means are higher than that, right? So you end up with a biased sample, and it's the exact same concept. Okay. All right. I'm conscious of the time, and I've kind of blathered on there for about 5 to 8. So I think I want to get into all this though before we move on. So I'm very quickly just going to talk a bit about adding priors. We will get to that later, but just because it's a very natural point. What we're trying to do though is, rather than using this uninformed one, we're going to talk about where we add priors. So essentially what we're saying is, like I mentioned in the data generation, rather than saying, every single lambda is separate from one another and it is, anywhere value from 0 up to infinity, we're not going to say that. We're basically going to say that every lambda is a draw from a gamma distribution. And that gamma distribution is, has parameter values, which we're going to pass in as data. And then we're going to draw inferences of that. And that can be really, really powerful for a couple of reasons. But one of the main reasons is it allows customers for which we have lots of data to inform us about customers for which we don't have a lot of data. And that's kind of called partial pooling. And, that's one of the powers. That's where we start going down the road of what are called hierarchical models, where we can use these kind of partial pooling effects to get some idea of how all this goes. So I'm going to leave it there for a few minutes. I've seen it's 5 to 8. What I'm going to do is go back up. Let me just go here, and we're going to talk about how visual diagnostics. Yeah, I want to talk about these a little bit. So when we come back, I'm going to take a break there. We'll come back about 8:05. I'm going to give everyone 10 minutes. I'm going to put myself on mute and I'll probably turn off my camera. But if before I do that though, and before we take a break, I will say if anyone has any questions or needs me to explain anything, now is a great time to do it. Because like I said, I'm giving people 10 minutes, but it's mainly just to give everyone else a break. I'm more than happy to use that time to talk about stuff. But when we come back, we'll talk a little bit about some visual diagnostics for sample validity and kind of how you check if your sample is valid, like what are the things you do. And yeah, and then we'll talk about a bunch of other things that we're going to do in terms of, you know, trying different values. And we'll talk about adding priors and all that kind of stuff. All right, so I'm going to stop there. If everyone's, I'll see you back at about 8:05 in about 10 minutes time. But like I said, if anyone has any questions or wants me to go over anything, now is a great time to do it. But yeah, thank you very much. And I'll see you back in a few minutes. All right, I'm back. Like I said, I've got 5 minutes before we'll start back up. So if anyone does want to ask any questions or use that time, now is the perfect time. No one got any questions? All right, I'll give people another minute or two, and then we can get started back up. Okay, all right, so let's start back up. All right, so like I said, we've ran our Stan model. We've set up our likelihood model. We've said, each one is a Poisson. We're going to get a frequency for each one. We've ran the model and we're running our diagnostics. We haven't found any of these issues. To briefly explain what that is unfortunately it's kind of like absence of evidence isn't evidence of absence kind of thing. So unfortunately, you can never prove that any given posterior distribution is a valid sample. But what you can do is show that it's absolutely not valid, and that's what these diagnostics do. So generally, when you're fitting a posterior distribution as a result of MCMC, you run a number of diagnostics on the posterior, and the key thing that you're looking for is a thing which is fancy sounding. It's called geometric ergodicity, and it's a necessary condition for your sample to be valid, but it isn't sufficient into using that kind of mathematical parlance. So if a sample is not geometrically, or if you don't have geometric ergodicity, it's definitely invalid. But if you do have it, it's not valid. And what it boils down to is a lot of the theoretical guarantees of things like MCMC all work in when you take limits to infinity. So when you've got an infinite amount of data, these things work fine. However, in the real world, we're dealing with finite samples. And suddenly, just because something works when it goes to infinity doesn't mean that any given finite sample will be valid. So essentially what we have is a bunch of diagnostics that allow us to at least check to make sure that you try as kind of concretely as possible to show that all the tests for things being invalid are not there. So therefore we assume it's valid. And that's kind of the best you can do. So there's a bunch of things. Now, the reason what geometric ergodicity basically means is that any given stretch of the sample comes from the same distribution. That's kind of like, in other words, if you're and the simplest way to think of it is a trace plot. So a trace plot is essentially, we have like in our sample from our posterior, we have a whole bunch of iterations, which are, you know, the sequences of the Markov chain Monte Carlo. So we just plot them by like ID number. And what we want to show is that it's essentially a flat line around the value. So you get what are called these hairy caterpillar plots. Now, to explore as much of the space as possible, we generally have multiple chains. So we set, which is why it's called Markov chain Monte Carlo. So we have these multiple chains that explore different areas of the posterior space. I'm running 4 chains here, so you can run 8. You can run as many as you want. Generally, you from practical points of view, you generally want, you run 1 chain per processor. And then, so let's say you're doing 2,000 iterations in your sample, you have 4 chains, each chain is 500 length, and then you combine them to get your sample. Okay, so what we do is, we also want to show that each chain is kind of exploring the same space as each other chain, because if it isn't, then you've got chains that aren't allowed. Basically, this chain is over in this part of the space, and this chain is over in this part of the space, and they're not mixing across each other, which is also why it was referred to as mixing back in the day. We basically want to make sure that all these things, so these are kind of checks we do to make sure that our statistical sample is valid. And this is it's called a trace plot. So we're including the first half of the iterations, which we usually throw away. That used to be called the burn-in, and it was about finding the target distribution. Nowadays, that's not so much the issue because we're using more advanced algorithms, but we still have what's called the warm-up period, which isn't so much about finding the area of the typical set, it's called, which is kind of the part of the posterior distribution space we want to sample from. Because of the new techniques, which I'll explain probably in a later workshop, or probably the next one. But it uses that warm-up period to kind of do a whole lot of parameter tuning so that the actual sampling is done as efficiently as possible. And you can see here, when we include the warm-up period, certainly at the start, you get all these silly values for each lambda value, but it very quickly settles down around the final value. And if you look at these trace plots, you can see, apart from the first part, they're all kind of bouncing around the one value. All 4 chains are. And this is what you call a hairy caterpillar, because it kind of looks like a hairy caterpillar, right? But later on, we can actually get rid of the warm-up period and just look at the sample itself. So you can see there, like lambda, and I've just taken, so that we could create a trace plot for every parameter in our posterior. Now remember, it's like with 1,000 customers, we have 1,000 parameters. So that's not really practical. So I've just taken the first 6 and just showing what they're like. So you can see like lambda 1 for customer 1 there. You know, it's all going around what, let's say 0.3 and a half, 0.035. And then this one here is about 0.05 and so on. So we're kind of getting these are the things you want to see. But if you have an invalid plot or if you have problems with your model, what you will see is when you do this trace plot, you'll see like one chain. I don't know. Can you, Neil? Are you still here? I don't know. Yeah. Can you see my mouse? Can you see where my cursor is there? Okay, thank you. So if you can see, like, you might have one chain that's kind of up here and another chain that's down here. So what that's telling you is that the two chains are exploring different parts of the parameter space, and essentially that your sample is invalid somehow, and you've got to fix your problem. You've got to fix that model. Here you can see all the chains are kind of on top of one another, and they're all kind of moving around the same value. So that's what tells us that our sample is, it's indications that our sample are valid. So that's one thing we can look at. We also want to look at the R-hat. R-hat is this kind of MCMC diagnostic, again, created by Andrew Gelman and a bunch of others, where they look at the autocorrelation in the Markov chain Monte Carlo, and they're essentially splitting it, which is why it's called the split R-hat. And essentially you want the R-hat to be around 1, and you definitely want it to be less than, it used to be 1.1, but they've kind of made that stricter now. They kind of want it to be definitely lower than 1.05 and ideally less than 1.01 for like proper validity. And you can see that's just taking all the 1,000 parameters and it's plotting the R-hat value. In some cases you actually have it less than 1, which means that you have more information. But R-hat less than 1 is actually good. But most of the time you have an R-hat greater than 1, but you just don't want R-hat to be too big. And if you have a really bad model, you'll have an R-hat of like 1.3 or 1.5 or 2 or 3. And in that case, essentially what it's telling you is that your sample isn't particularly useful. So those are a couple of things we look at. Effective sample size is related to the R-hat value. So basically what's happening in Markov chain Monte Carlo, each sample, because it's a statistical thing, there isn't necessarily a full data point worth of information in every data point, because you have, you've autocorrelation because of the Markov chain. And if there's the higher the correlation between each point, then the less information each additional data point gives you because of that correlation. So essentially, you can turn that R-hat value into a ratio of the effective sample size, which is how many samples do we effectively have, even though let's say our sample size is 2,000, our effective sample size might only be 1,500 because of this autocorrelation. And this is just a plot of that. So we can see in all cases we actually have, and you want that ratio to be around 1 or better than 1 if possible. Anything lower than that, like if you start getting sample sizes very low, it's telling you that at least some of your parameters are problematic and you need to fix them. And that again is showing us this is kind of what a sample. Now, when you're doing this, you do need to do this for all your samples, but you don't necessarily need to report it all the time. You just kind of only report it if there's a problem and you want to discuss it. And then once you've got your fit, you might put in 1 or 2 just to show for the sake of completeness. But you do kind of need to check, a list of these things. Another one to look at is the autocorrelation. So it's just a correlation plot. And again, what you'll have is, relatively high autocorrelation initially, which you would expect, but at different lags, it will drop off very quickly. And you can see we've got, again, the 6 lambdas. We're looking at the autocorrelation within each chain. And you can see, in all cases, it kind of drops off after 1 or 2 lags, which is pretty much exactly what we want. And like I said, we don't necessarily need, a comprehensive articulation of all of these diagnostic plots, but it is very important to actually check this, and check all these, because if our fit is not valid, then there's no point in actually checking the goodness of fit of the model, because we know that the sample we've obtained is not actually representative of the sample we tried to, sorry, let me rephrase that. We run a stand model, we get some answers back. However, if that sample isn't a statistically valid sample of the posterior, then there's no point in doing any like goodness of fit checks or anything, because the sample we've obtained isn't the sample we tried to create because of all these problems. And we've got to fix that problem first before we move on to the next step of, well, okay, we've got a statistically valid sample, but is it any good? right? And they're, like I said, so we've now got this additional step in there that we need to worry about. Now, as a quick aside, and I'm conscious of time, but the question you might ask is, well, why bother? Like we seem to be bending over backwards to do something that seems kind of cool as opposed to useful. And while there is a certain element of truth to that, I will also say that even in the maximum likelihood area, you do have this problem, but it kind of gets obscured by the fact it's an optimization, so you're only looking for a single point. It doesn't actually make the problem go away. It just kind of hides it because you're dealing with optimization rather than trying to map out an entire geometry. And also, the very major gain that we get from all of this, like I said, is we're also capturing all the parameter uncertainty in our model. So to me, this trade-off is very good because it also helps you understand what you're trying to do. And it also means that you really have a good understanding of how these things work. And much more importantly, when they don't work. And if it's a problem, why is it a problem? And how do I remediate all these? All right, so what I'm doing now is we're going to check the model fit. Now, as I said, for every customer, right, we now have a posterior distribution. We have our sample contains, I think, 2,000 iterations. So we now have 2,000 data points for each customer lambda, right? So every individual customer now has 2,000 data points, which are the posterior sample of that customer's lambda as inferred by the data, okay? However, as I mentioned before, because we have synthetically created this data, we know what the true value was for creating that data, okay? If you remember that, because we like I said, when I got the question earlier on, we had 1,000 customers. Every customer was assigned a lambda value. That lambda value was then used to generate the transactions. We then had a summary of how many transactions were generated by that synthetic process. And we were using our model to infer the rate back from the number of transaction count we observed, okay? So what we would expect is that if we look at the distribution of values for lambda, because we know what the true value of lambda is, we would want to make sure that essentially that posterior distribution is a good representation, like contains the original value somehow. Now, basically, we don't expect every single posterior to be particularly representative because sometimes you just get wacky results. Like if you have a normal distribution, right? Sometimes you will get a value, like I could have a normal distribution that has a mean of 0 and a standard deviation of 1. But every so often, you will get a value of 3.5. Now, it won't be very common. It'll be, 1 in 100 or 1 in 300 or whatever. But if you're dealing with like 1,000 customers or 10,000 customers or 4,000 customers, if we have a lambda value that has a range between, say, 0.1 and 0.4, every so often, with a gamma distribution, every so often it's going to throw out a really, really high or a really, really low lambda value. And that's then also, on top of that, we're also going to get weird results. So you could have, over a period of a year, you could have a transaction rate of 0.1 per week. So 1 every 10 weeks. So we have 50 weeks in the year. We'd expect to see about 5 transactions. You could very easily have a customer that has 1 transaction or none in the entire year. They just never transact. And as a result, we wouldn't actually have any, the posterior distribution that we're going to recover for that customer is probably the true lambda value is going to be in one of the tails of that, right? Does that all make sense? So basically what we do is what we want to do is, it's kind of like a QQ plot. What we're doing is, for every particular customer value, we're going to create an empirical distribution based on the posterior. So we have 2,000 values. That is our posterior distribution for lambda. And this is for one customer, right? So for any given customer, we have 2,000 values, which are the posterior sample for lambda. We create an empirical distribution from that. So there's an ECDF. And then we see where does the true value lie on that ECDF. And that gives us a Q value, which is between 0 and 1. So for every customer, the true value turns into a Q value. And if our model is doing a good job, that each customer's Q value should form a roughly uniform distribution. Does that make sense? So essentially, every customer has 2,000 iteration sample of its posterior distribution, which should contain the true value. But we now know what that true value is, so we can put that in the distribution and get an empirical value from 0 to 1. Right? Where is it in the distribution? Right? And that will give us a Q value, and then we'll have one of them Q values for every customer. So we're essentially combining the posterior distribution of lambda with the true value of lambda. Now, we can't always do this because we don't normally know what that true value is. We only know it when we generate the data synthetically, and that's why we went through this whole rigmarole in the first place, right? And then, if that gives us a uniform distribution, we know that we're at least on the right track, that the model isn't completely mental, that we haven't created like a model and a data generating process that cannot even recover its own parameters. Now, this is something that has kind of been done and systematized by people, especially in the STAN community, over the last few years. They call it simulation-based calibration. So essentially what you try to do is, when you're building any kind of a STAN model, you actually use the model to generate data, and then you fit the data, the synthetic data, using the STAN model and try to recover the original parameters. And if you can't do that, it's telling you that there's some kind of problem within your model before you even add external data in, right? So that's basically what we're trying to do here. We're trying to say, like, essentially, are we doing something mental that isn't going to work, is kind of dead on arrival, and are we just wasting our time? So we can see here, you know, and again, we wouldn't expect it to be perfectly uniform, and there is kind of a trend where we seem to be getting lower values, you know, it doesn't seem fully uniform to me. We do tend to have this trend towards, we're biasing towards lower values of the lambda. Now, there's good reasons for that, and it's basically the way I fit the model. Basically, what's going on there is when we fit our model, let me just scroll up here a bit. We're not really using the true value. We're using this TNX weeks is what? 0 and 1, Marion. So sorry, I got a question here is, so let's say we have a quantile that is, we have an empirical distribution that's goes from say 0.1 up to 3, and the true value is 4. What does the ECDF produce? Well, in that case, it would produce a 1, because it basically, if it's not inside the body of the data, the value will either give you 0 if it's lower than the lowest value, and it will give you 1 if it's greater than the greatest value. Okay, so you will get a few of them in there, and we will kind of expect that because we're not necessarily getting a full probability distribution, but our uniform plot of the Q values should give you that. Now, I'm using the, again, I've done all this stuff in R. I'm not quite sure how ECDF's, its stats models work in Python. I think it's something similar though, because I think that's how an empirical CDF should work. So if it's basically 0 probability if it's lower than the minimum, and it's a probability of 1 if it's greater than the highest value in the sample that's used to create the ECDF. Okay. All right, so does everyone kind of follow what's done there? So we've created a plot here. I've scrolled it up once. So I think so it's hard to say exactly what's going on there, but I think it's this transaction weeks in the data. Let me just scroll it there. I've kind of done a few things, and I'm gonna, I'm using kind of the full data set here. So where is my data? Just give me one sec. Yeah, I'm fitting here. So all weeks is basically the 52 weeks in the model. All right. So I'm assuming that there is 52 weeks in the year, because I know from my synthetic point of view that I gave every customer 52 weeks to transact, right? So I've included that in there, and you can see, so there's, while there is a slight bias on the downside, it's not doing too bad. But what I was trying to do here with the observed time frequency is I'm actually changing that. So rather than fitting in 52 weeks for every customer, or whatever it is. I think I divided, the final date by the full date and then divide it by however many weeks. So I think it's 52 point something. However, in the real world, again, like I said, when we start thinking about things like customer churn and, how things work and like real life issues, we can't really necessarily do, an a priori time period. Instead, what we have is we know that the first period the customer transacted and then the last time the customer transacted. And that's kind of our estimate for the period of which we observe the transactions. Now, we know that's kind of wrong because we also know in reality we would have, just because the last point of time in which the customer transacted doesn't necessarily mean that the customer churned at that point. It probably churned sometime after that. But for the purposes of this, we're ignoring it. But what I wanted to do was, let's fit a similar model, but now we will just use the empirical observation of time. So rather than using a constant period of transactions, we're going to use this essentially lower bias. And what does that run? And we kind of repeated our process. So we see we get a much heavier bias to the downside there. So what's happening there is our quantile plot is going to the lower side. So our posterior distribution is biased up because the denominator is lower. So as a result, it's essentially shifting up the Poisson distribution for each customer. So as a result, our posterior distribution is being pushed to the downside much more markedly than with our observed plot. So we have this kind of issue that if we used an observed time, and this is something we're going to be paying attention to later on, how do we kind of deal with this? This is kind of, we've got essentially an inherent bias in the data set because we don't have a proper view of, in the real world, we're not going to have a proper view of the full period of time over which transactions could have occurred. Does all that make sense? Because we have explicitly kind of ignored the whole churn thing. But once we start thinking about that, we're going to have to account for that in our modeling. And it has a real effect. We can see now that, this should be a uniform plot, but it's kind of not, right? You can kind of see that there's a bias here to the downside, which tells us that our posterior distribution is biased upwards. There's a high bias on our parameters. So our posterior distribution is tending to overestimate what the actual frequency rate is. Okay? Can everyone see that? Have I kind of explained that? All right. And now we're going to construct some comparisons. So basically what I've done is I've taken the fixed time model where we're using the full 52 weeks. And I've also got the observed time model, which is where we're basing the time period as from the start of the year to when the last observation was. And we're just plotting the two posterior distributions side by side. Now, so if you look at these, I've taken a sample of, I don't know how many customers we have there. I think it's 30 or something. Let me just quickly check the code. And again, all the code is, it's 30 customers. So, and what we've done is we've taken the 80% interval of that posterior. So we have a posterior distribution for each customer lambda, and we're just taking the middle 50% and the middle 80%. So we're looking at quantiles 10, 25, 75, and 90. And we're kind of, the 50%, the middle 50% kind of makes sense, right? It's between the quartiles. But the reason why I've gone wide out into the tail is because the tails, that when you start going out into the tails, the quality of the sample tends to be, the quantile estimate out in the tails tend to be very, very dependent on the sample. So you can end up with very, very unstable estimates out there. Whereas by going to 1090, we're still covering 80% of the probability distribution. So it gives us quite a good range. And by comparing the 50 and the 80, we get a good sense of, the shape of the distribution. And then I'm just plotting everything against the true value, which is the lambda. And we can see here, in some cases, our true value is above where it's observed. So we can see for this customer here, we can see in some cases it's above it. Sometimes we're getting in the middle. But in general, we can see that there is a difference between not for all of these, but in some cases, the observed time has a tendency to be above the fixed time. And that kind of makes sense, right? Because we've always got 52 weeks in the fixed time, but when we're dealing with the observed time, we've got less of that because it's a smaller denominator, and that it can't be any higher than that. So we're introducing a bias there, and that's something that we're going to have to account for later. Okay. All right, and then estimate posterior cover. Yeah, so we're looking at kind of how often the true value of lambda falls within our posterior intervals. So what we're doing here is we're taking every single customer. We're basically saying, is the true value of lambda inside the 50% interval 50% of the time? And what is the proportion of times that falls within that? And what doesn't it? And we can see here that so 50% for the fixed time model, it falls inside for every customer. So each customer is a different true or false value. So half of the customers, it falls inside the 50% half of the time. So that's good. It would be bad if it wasn't, because it meant we didn't have a good calibrated distribution. And 80% of the time, it pretty much falls in 80% of the time. So the fixed time model is actually doing quite a good job of capturing the uncertainty. Okay. Whereas the observed time model, it only falls within the 50% range 42% of the time. And it falls within the 80% range 71% of the time. So we can see the coverage of the observed time isn't as good as that of the fixed time. And that's what we would expect. Because as we said, we have we've almost systematically introduced a bias into our model by using the observed time. So the reason why I'm doing this is, I know this is a bit convoluted and it seems a bit weird what we're trying to do. But again, like I said, we're kind of using these toy models to build intuition for the real models that we're going to be building. And what this is telling us is that, at least for a first pass, we're doing an okay job, at least from the point of view of initial models. We're doing an okay job of, certainly with a fixed time model, we're doing a reasonably okay job of being able to recreate the input parameters that we used. Okay. All right. Okay. Anyone got any questions about that? We're at 8:30, so I've got about. I won't try and run to the 9 o'clock. Those of you who know me by now, I try to finish around kind of 9:45 to the hour, and also that gives opportunities for questions if you have any. Does anyone have them before I move on? Okay, I'm going to move on, but like I said, if you have any, pop them in there. I will get to them as soon as I can. All right, so all of this was very well and good, right? Again, we hadn't really added any priors, but now what we're going to do is basically start thinking about what we're doing a bit slightly more carefully. So like I said, we had these implicit uniform priors in our previous model because we weren't explicit about creating a prior. So essentially what it does is it assigns an equal probability to every possible value given by the constraints of the parameter. So in this case, because we've created a lower bound for each transaction rate, basically any value from 0 to positive infinity is equally likely at the start, right? But we kind of know that that's nonsense. We kind of know that those values aren't feasible. It's not really feasible for a customer to have a transaction rate of like 10 million or billions of a transaction rate. We kind of know that's nonsense. And this is why uniform priors are generally bad for models. So they kind of, at first pass, they think they're really good because, we're letting the data do all the talking. But in reality, we have prior information that we kind of want to use. We know that some of these values are nonsense, right? We know that it doesn't make sense. In reality, a lambda value shouldn't ever go more than, say, 10. I mean, we could have it. It means 10 transactions a week. That would mean if you're only working like 5 days a week, it's, 2 a day. That doesn't seem like depending on, I mean, I guess it would be possible in certain businesses, but in this kind of space where we kind of know that's nonsense. Most customers, like highly frequent customers, transact 2 or 3 times a week. And even that's quite rare. It's more like once a week, right? So anything above 1 is like unlikely. So the vast majority of lambda values were between 0 and 1, averaging around 0.25. So like 1 transaction a month. Okay. So we're now going to, we now basically want to create what prior distribution do we use? And The power of Stan is we can use any of them. We don't have to go with conjugate priors, but we will in this case because it's nice and simple and it kind of makes sense. It's a nice kind of way to think about it. So if we simulate a gamma distribution from 1 to 4 and then just plot it to see what it looks like. And this is useful because when coming up with priors, sometimes it's useful to just try out a few values, plot the distribution you get and see, do the kind of values you have in your head make sense? So if we're going to use a gamma 1, 4 parameters, right? Okay, well, what values does that give us? So we simulate from the data, and again, I've got some code there, but we're not doing anything particularly clever. We're just sampling with the gamma 1, 4, and it's giving us a range of customer values, and we can see, you know, okay, there's loads from 0 to say 0.5. Most of the distribution is in that range, and then, you know, there's another chunk going from 0.5 to 1, and then it kind of tails off, and nothing is really going bigger than 2, or certainly 2.5. Okay, now as we increase the sample size, this tail will get bigger and bigger, and that's fine. But, you know, from an intuitive point of view, we can see that this is probably not an entirely unreasonable prior distribution for the customer lambdas, right? So let me just stop here to explain what we're doing here. Because we're using kind of priors, right? What we're saying is that there's essentially 2 levels going on here, right? There's 2 levels of uncertainty. There's uncertainty around the lambdas of the customer, and then there's the uncertainty around how many, like the discrete process of the Poisson distribution, right? That's why it's called a hierarchical model, because we could also make inferences about that lambda distribution, which we will be doing down the line, right? But right now we're not bothering about that. We're just setting these values in advance. We're not allowing the data to actually sample from the hyperprior. We're actually fixing that prior. So we're creating a fixed prior, and it's a gamma 1, 4, and then we're building another model from it, right? Perhaps we might want a bit more probability. We can basically change the scale a bit. So we drop it down from 0.25 to 1, and we end up, you know, with a big chunk down here, but we get slightly higher values. And like I said, this distribution looks a lot more skewed, so we just plot it on a log scale. You know, how does this work? All right, so let's just try it. So the first thing we need to do is we've got an almost identical Stan model, okay? But now we're adding extra parameters, extra data into the model. So we could just make this gamma 1 and 4, but it's kind of handy to pass in these prior values as data, because then we can use the same model and different priors to get different fits, and then compare the effect of different priors on our model. Okay, and that way we can kind of get a sense. It gives us a bit more power over what we're doing. So it's kind of a fudge in a way, because this isn't really data as such from a conceptual point of view. But as far as Stanning is concerned, it's the same, right? It's just it's values we're passing in that the sampler is going to use to create a posterior distribution with. So we're passing in this R and alpha. And now we have this extra line, as well as this, you know, this target plus equals. What we're also saying is that each lambda value, and this is vectorized code. We don't need a loop for this because Stan has vectorized all this code for us. We're basically saying each lambda is drawn from a gamma distribution parameterized by R and alpha. Okay? Does that make sense? And then each lambda is then going as we did before. So we've now put a distribution, a prior distribution on these lambdas. We now compile the model and we fit it. And we, you know, check all our diagnostics. You know, everything looks fine. But now we can compute our prior distribution. And we see now actually that while there is a slight bias before, it's actually better even than it was before, right? You see that? We actually have something that looks actually more uniform than our flat model did. And that kind of makes sense, right? Because with our flat model, we were basically saying that, you know, we were basically saying that it was reasonable to have extremely high lambda values that were then being kind of curbed in by the data. But now, even if you don't have a lot of data, you're not going to give ridiculously high values for lambda. We're kind of compressing it in. And you will often find that actually that setting priors gives you more realistic values, because now the problem you can often do is, and this is where things can get a bit sketchy sometimes in terms of, because you can essentially use the data to set your priors, You generally don't want to do that. A better way of doing it is to try and use your prior knowledge to set your, so you come up with very, very broad numbers that aren't necessarily representative of the data, but are still feasible from a conceptual point of view. So in this case, ignoring the data, we would know that, lambda values of greater than, 10 are virtually impossible. So therefore, we maybe will use, that's 0.25 and 1, or 1 and 4. And then we can kind of fit them all. And then once we've done all that, we can start plotting them against each other, right? So now that we have posterior distributions based on the observed, it's useful to compare them. So we're going to compare the flat model against the prior model and just compare the two. You see, broadly speaking, and on the other thing we've done is we're kind of comparing based on the values, we're segmenting our data set to different groups of known values of lambda. So what we're trying to see here now is we've kind of bucketed all our lambda values into a couple of different segments. And we're trying to see, like, do higher values of lambda get dealt better than lower values of lambda, or is there any kind of issues with our model here? But in general, we can see that, broadly speaking, things kind of look the same. And we want to compare the two distributions for posterior coverage. So we can see the flat model. And again, we're using the observed time for both of these models. I'm not using the 52 weeks. I'm using the observed time because that's, like I said, we're dealing with more realistic limitations of what we'll be able to do. There's no point in having a really great model that then has inputs that are not going to be feasible when we go to the real world. And yeah, we can see that actually the coverages are better and closer to our, so even though we're using this biased observations of time period, using a prior actually helps us get more realistic values and gives us a better posterior distribution as indicated by these values. Okay. Again, we can fit a narrower prior, so we're going to do the same thing. The previous one was allowing for higher values. I'm now going to use a prior 2, which is a 1 and 4 input into the model and see what we get. And again, we're doing all this and create our comparison plots. So for segment 1, yeah, we're getting a few kind of weird values where we know the frequency rate is a bit odd. I'm not quite sure what happened there. But, we're creating comparisons, on prior 1 and prior 2, looking at the coverage. Yeah, there's not much of a difference really between the gamma distributions there. The main thing is the fact that we're using a prior at all, as opposed to, do we allow extreme values or do we not allow extreme values? Okay. All right. Well, that's kind of where I want to end it because it's 8:45, and I appreciate, I've been talking a lot and I want to make sure that I've kind of brought everyone with me. So I'm going to leave it there. I'll talk about where we're going to go now. I don't know if there's going to be a workshop next month because I'm hoping to have a talk. A guy, I actually need to ping him tomorrow and make sure he's still good to talk in April. And we're not sure exactly what, I think we set a date, but I want to confirm it with him again. If we do, we're also hoping to have an in-person talk in May. I'm not exactly, it'd be one of the three of, it'd be myself, Pedro, or Richie. I'm not exactly sure who yet. But I might run, I'll definitely run a workshop one of those 2 months anyway, because I don't want to leave it too long before we get back to this. But what we're going to do in the next workshop is start properly building hierarchical models. So rather than, setting a prior for lambda, what I would like to do is actually make the prior distribution for these customer lambdas to themselves be parameters of the model, so that rather than trying to, mess around with those priors, we actually allow the data to kind of set those values, and that's where we get these hierarchical models. And instead, we kind of set parameters for those parameters, like, we set a distribution of possible values for that value, so that we basically move our uncertainty up a level, and it allows us for the data to speak a bit more about. So essentially, the way the Bayesian approach typically is that you capture your actual uncertainty with a posterior distribution. So because we don't necessarily know what the parameters of that value is, we make the parameters of that prior themselves be parameters of the model. So we kind of move the level, we move the uncertainty up a level, because we can be at the higher level, we can be a bit more certain about roughly what it's going to be. And then we let the data fit the model for us. So that's kind of where we start building hierarchical models. But the flip side of that is the whole Stan power tool thing kicks in. And that's where we start to much more easily start looking at issues with divergent transitions and all that kind of stuff. And we will talk about all that a lot more next in the next workshop. But that's pretty much where we got to. I'm going to stop the actual content there, but I am going to hang around for a while. What I might do though is, thanks very much for coming, by the way. I hope you found that a bit more informative. I'm very conscious that we haven't really gotten to anything cool. We haven't done anything particularly sexy. All of this is kind of still very basic stuff. However, I am very firm believer that it's very important to cover the basics of this really well, because if you don't do that, it's really, really easy. When you start trying to do this in anger, suddenly the real world starts throwing up all these roadblocks like hard to diagnose diagnostics, and you get divergent transitions, you can't figure out why, and what are we doing here? And you basically, your lack of understanding and uncertainty jumps up and punches you in the face. And the reason why I'm saying that isn't to be in any way condescending, because these are all the issues I've had in the past. So what I'm trying to do is kind of help you avoid, like, basically understand the various things that I've learned from this. But the flip side of this is, once you actually start to understand this, it can start to do some really, really cool and powerful things that aren't really available using from other methods. This stuff is really, really powerful once you kind of wrestle with it and start to understand it. So what I'm going to do there is I'm going to stop the recording now so that people can freely ask questions.